Okay, guys, we are going to talk today about the third method for solving linear systems. It's called the elimination method. Some of you are going to be like, oh, Miss Egan, you should have shown me this from the beginning. But there's a progression. We need to know how to graph things. We need to understand substitution, and we need to understand elimination, because depending on the situation, all three methods are valuable, even though they are being used to find the same thing. So again, put your name up here. We're going to make a copy of these notes for you to put in your math notes folder at the end. Go to page 2. So solve linear systems. We're going to make this a little bit bigger here. Old lady eyes need to see. So we're going to talk about, like, what are the steps first. So with substitution, it was all about getting one of the variables isolated, right? We needed to do that first. Well, with elimination should tell you something right there. We're looking to eliminate one of the variables from each equation. And of course, we want it to be the same. So we want the x's to eliminate out or the y's to eliminate out. And in math, in order to eliminate something, when you're talking about addition, subtraction, means that they have to be additive inverses. So if you're looking to get rid of a 3x, a negative 3x gets rid of it. If you want to get rid of a 7y, a negative 7y would get rid of that. So part of what we're going to need to do is we have to check to see if that exists in the equation. And if it doesn't, we're going to have to do some work on one of the equations, or sometimes on both of the equations, to be able to make that additive inverse occur. And we're going to do that work using the golden rule, which tells us do onto one side as you do onto the other. So I can take a whole equation and multiply it by 3, and it's still the same equation. Or I could divide it by a -2, and it's still the same equation. So let's go ahead and write our steps in down here. So step number 1, we want to write the equations in the same form. So we're going to write both equations in standard form. So standard form being ax plus by equals, I need the equal sign, equals c. With one caveat. Usually with standard form, we do want the coefficient a to always be positive, and a, b, and c are not supposed to be anything but integers. So it may not matter when we're doing the elimination method. We don't need to worry if a is positive or negative to start off. We don't necessarily need to worry if there's decimals or fractions. Sometimes we're going to eliminate them to make our job easier, for sure. But the point is that we want to see everything lined up from each equation to see if we have any ability to eliminate stuff. Okay, so step number 2, and we're going to put if needed, right? So maybe we'll make that in red, so we know this is a if needed. Switch that back to blue. Remember, you guys can be creative with your color coordination. Multiply one or both equations by an integer. So one set of variables will eliminate. In other words, we need additive inverses. Of course, I didn't spell eliminate right, so Do I spell that? Eliminate. Okay. Step 3. We want to add the columns like the column. So we're talking about combining like terms. But instead of doing it all within one equation, we're looking up and down between the two equations. So combining like terms. And this should eliminate a variable, right? That's the whole purpose of step 2. Okay, should eliminate a variable. So that we can solve the equation for the remaining variable. So if you remember, for a system of equations, we need to find the value of both variables. We need to know what x is worth. We need to know what y is worth. So when we say we're eliminating the variable, we're not talking about not having an answer for it. We're talking about making an equation in one variable that we know how to solve. So once we solve the equation for that variable, we now have an answer. We now have half of our coordinate pair. We have our x or our y, or we should know if it's a special situation. So if we have a value for x or y, we then have to go in and do step 5, which is substitute answer from step 2 or step 4 and solve for the second variable. We're going to put, since we're kind of running out of space, we're going to put it right next to it. We're going to put number 6. Right? Check your work. We're going to check our work the exact same we did in substitution. In fact, when we look at this, the difference between what we're doing here and what the substitution method is really this idea of eliminating a variable. In substitution, we do it by solving or isolating a variable and putting that expression into the other equation to make it a one variable equation. Here, we're going to eliminate one of them. And then we're still going to solve the equation for the remaining variable using our 5 steps. And that kind of thing. So let's keep that in mind. Let's go and see if I can minimize this. My old lady eyes are going to be not thanking me. Nope, a little. I'm going to go with 11. I'm going to go with bold. And that's just so that I can all fit in there nice and neat for myself. So let's go up and look at example 1. So in example 1, we have negative 5x minus 6y equals 8. 5x plus 2y equals 4. So when they're talking about columns, we're lining things up. That's what the standard form does. So we have our x's above our x's, our y's and our y's, and our fixed numbers. So I'm going to look at these up and down in the column. So right now, a negative 5x and a positive 5x. Those two are additive inverses. They'd eliminate out. Negative 6y, 2y, not going to eliminate out, not going to eliminate out. So let's go ahead and start our work. I don't know if I forgot that or not, but if I forgot it, I'm going to grab one of these copies down here. I'm going to copy this. I'm going to paste it up here since my text box has disappeared on me. And I'm going to paste one over here too since that one's moved. I'll have to do that as well. So I'm going to go right in here and I'm going to do my work. So one thing I should notice is essentially if I put an equal bar underneath this, no, I'm not going to do that, but if I added the columns up, the x's are going to be disappearing, and negative 6y and 2y are going to leave me with negative 4y. equal to 8 plus 4 is 12. Now this is a pretty basic equation. Simply divide both sides by -4. And lo and behold, I find out that y equals 12. So I'm going to take that 12 value and substitute it back in. I'm going to come back over here. So this is really step 1 was kind of completed for us. This is step 2. I've added the columns and I've solved. So I'm actually going to put there 1 and 2 were completed for us. This was step 3 and 4. And so I just have step number 5 left. I'm going to do that over here. Substituting that y equals 12 back in. I pick one of the equations. It doesn't really make a difference. I'm going to go with the bottom one. So 5x plus 2 times 12 equals 4. Box a little bit longer. So I'm still going to have 5x. 2 times 12 is 24, equal to 4. I'm going to subtract, do the opposite, subtract 24 from both sides. And I'll end up with 5x equals -20. And if I divide both of those by 5, I would get x equal to -4. I'm going to actually put it over here just because I didn't have room. So my answer lines up to be -4 as my x and 12 as my y. And then I should go ahead and check my answer. And because of lack of space, I'm just going to do it, in my head. So I substituted into this one in step 5. So I'm going to use this one. So -4 times -5. 2 negatives would give me a positive. 5 times 4, that would be 20. Then -6 times 12, positive 12. So that's going to be a negative. So 6 times 10 is 60. 6 times 2 is 12. So that would be 72. So I have positive 20 minus 72. Oh, I made an error right here, right? That y value isn't 12. It should be -3. That was like a major snafu. So I'm going to make this a -3. A good thing I checked my work because I saw that I did it wrong. And over here, I have to make this a -3 and go back through and correct my work. So this is going to become -6. It's going to become -1. Actually, +6 is what I'm going to take away from both sides. Which means 5x would equal +10, making our x value 2. Let's check this answer. So 2 times negative 5 would be negative 10. And negative 3 times negative 6 would be positive 18. So negative 10 plus positive 18 would, in fact, be equal to 8. So my answer is correct. Just going to change the color on that so I can see the answer. So I'm going to make that red. Let's go over here to example, we'll go down, I guess, to example 2. So negative 6x minus 4y equals 14, and negative 3x plus 4y equals 1. So here, positive 6x, negative 3x, not additive inverses. Here, negative 4y and positive 4y, yeah, they would eliminate. So these eliminate, and 6x minus 3x would be just a positive 3x. So let's go ahead and, I'm sorry. We know that 1 and 2 have been completed for us, so this is actually step 3, 4. Where we know we have 3x now equals 14. Looks like a cursor there, but it's just 14 and 1. So 14 plus 1 is 15. And divide both sides by 3. And we would find out that x equals 5. Okay. So far for our answer, we have a value of 5 for x. So let's come over here and do step 5. We're going to put in 5 for the value of one of the x's. Doesn't matter which one, I'm going to put in the top. So 6 times 5 minus 4y equals 14. So I should make these boxes a little longer. So come and do my multiplication. 6 times 5 is 30. So minusing 4y equals 14. I'm going to subtract 30 from both sides. And I wind up with a negative 4y equals negative 30 and positive 14. That would give me a negative 16. And if I divide both sides by the y, or the negative 4, I'm sorry, I'm going to get y equals negative 16 divided by negative 4 would just be a positive 4. So coming back here, my answer, I'm showing 5, 4. Check our work by substituting that back in. I'm going to use this one. So negative 3 times 5 would be negative 15. 4 times 4 would be positive 16. Negative 15 plus positive 16 would give me 1. That would be a true statement. So this is a good answer. Yeah. Let's go ahead and look at example 3. We have 4x plus 3y equals 2, and 5x plus 3y equals negative 2. So looking, I don't have anything here that are additive inverses, but I do have ones that have the same exact coefficient. So this would be kind of easy to make one of them the opposite. And it doesn't matter which one. In essence, instead of adding, we're going to subtract, or we're going to change the signs of everything in the equation. We're going to multiply by a negative 1. So when I do that, I now create a system that is, say, 4x plus 3y. And it doesn't matter which one I multiply by negative 1. I'm going to multiply the bottom. Equals 2. I didn't do anything to that. And then I'm going to multiply everything by negative 1. So it'll be negative 5x plus negative 3y equals 2. Because negative 2 times a positive or negative 1 equals 2. So now I can see I can eliminate. So I'm going to go ahead and do that. 4x plus negative 5x is going to give me a negative 1x. And those are going to eliminate, and 2 plus 2 is going to give me 4. So just for the purposes of steps, this was step 2 and 3. So 1 was completed for us, and this is step 2 and 3. Where we multiply one of the equations and then we add the columns. And then you would think I'm done, but I'm actually not done because I don't want to know the value of negative x. I want to know the value of positive x. So I'm going to multiply both sides or divide both sides by a negative 1. And I'm going to find out that x equals negative 4 then. I've gotten half of my answer done. Let's come over here and do step number 5. We know x equals negative 4, so we need to substitute that back in. Again, it doesn't matter. So 4 times negative 4 plus 3y equals 2. You notice I'm using an original equation. I'm not going back to one that I made down here, like negative 5x plus negative 3y equals 2. I want to use one of the original equations to check my work. So 4 times negative 4 would be negative 16 plus 3y equals 2. Add 16 to both sides. I'm going to wind up with 3y equals 18. And if I divide both sides by 3, I get y equals positive 6. So I have x equals negative 4 and y equals positive 6. So let's check our work. Negative 4 times positive 5 would be negative 20. 6 times 3 would be positive 18. Negative 20 plus positive 18 will give me negative 2. So that is correct. And if I put it into the other one, it would come out exactly the same as well. Negative 4 times negative 4 is negative 16. 6 times 3 would be negative 18 or positive 18. So 18 plus a negative 16 would still give me a positive 2. So that is our answer. Now here in example 4, we have 5x plus 6y equals 50 and negative x plus 6y equals 26. And we really have like options here. Because this is a negative already, we can choose to multiply the bottom one by a 5, and that would give us a negative 5, which would make an additive inverse. Or we can choose to multiply this by a negative 1 and make these the additive inverse. Either way, it wouldn't matter. It would be 2 different ways you can do it. So let's go ahead and we're going to make this, we're just going to multiply by the negative x. So 5x plus 6y equals 50. And we're doing it basically because it helps us avoid making really large numbers. So negative x times negative 1 would be x plus negative 6y, because positive 6y times negative would be a negative, and negative 26. So then when I would eliminate those 6's, I would be left with 5x plus 1x would give me 6x equal to 50 minus 26. Well, 50 minus 25 would be 25 minus 1 more, 24. And if we divide both sides by 6, we get x equal to 4. I go ahead and substitute that in. I'm going to use the bottom, so I'd have a negative times 4 plus 6y equals 26. And I know that's -4, so I'm going to add 4 to both sides. And I wind up with 6y equals 26 minus 4 is 22. Am I doing that right? So I found 6x, 24, x equals 4. Putting in for x, so -4 plus 6y equals 26. Oh, if I add 4, right? Sorry, adding 4, so 26 plus 4, whoa, is 30. Kind of like when you know you're going to get a fraction, you always want to recheck your work a little bit there. And if I have 6y equals 30, if I divide both sides by 6, I'm going to wind up with y equal to 5. Giving me an answer for x, we determine that to be 4. And for y, we determine that to be 5. Remember, our coordinate points are always x and y. And I'm going to substitute that into that top one to make sure. So 5 times 4 is 20. 6 times 5 is 30. 20 plus 30 does equal 50, so we are correct. And I think I'm not going to do all of these, but I just want to talk about different scenarios here. So in this one right here, again, we have that negative coordinate, -1 in front of the x. So because these two aren't additive inverses, it makes it really easy to multiply this bottom one by 3 to be able to get that answer. And if we did all of the work, which we're not going to do all of the work because I don't want you guys to watch an hour-long video, but you can certainly go back and check your work if you would want to, just to make sure that you can get it right. It would be 5 and 6. So coordinate point 5, 6 is where these two lines would cross over on a graph. In this one here, we have 2x plus 5y equals 3 and 3x plus 10y equals -3. So not additive inverses, not additive inverses. But, you know, it's pretty easy to go from 5 to 10, right? If we multiply this top one here by a -2, we would get -4x plus -10y equals -6. So -10y and +10y, they would wind up eliminating out, making our life easy. So again, this is just a one-step multiplication. And if I did all that work, I'd come up with 9, -3 is my answer. Again, I'll leave that as one of the problems that you can, kind of do on your own to check and make sure you understand the work. So looking at example 7, 4x and -3x, not additive inverses, 5y and 2y, not additive inverses. And what's interesting is there's really no way that I can multiply either one of these by an integer to get the other number. Like 3 times any number is not going to give me 4. 2 times any number is not going to give me 5. 5 times an integer will not give me 2. 4 times an integer will not give me 3. So what I'm going to have to do is I'm going to actually have to multiply both the top and the bottom. Now, the golden rule says I do onto one side as I do onto the other. That means whatever I do to 4x plus 5y, I have to do to 35. Whatever I do to -3x plus 2y, I must do to -9. I don't have to do the same things to each equation. In fact, that's the whole purpose of it. I'm not going to be able to if I want to create an additive inverse. So in the first one, we're going to multiply that by 3. And the reason is that 4x and -3x, they're already opposite signs. I need those opposite signs to create the elimination. And 4 and 3, their smallest multiple is 12. So that's what I want to get to. How do I get to 12 if I have 4? I multiply by 3. So I'm going to take 3 and I'm going to multiply it by that whole equation, 4x plus 5y equals 35. And on the bottom, if I have -3, how do I get to -12? Well, I'm going to multiply by 4. The entire equation of -3x plus 2y equals -9. 9. So once I do that, highlight that there, and I'm going to make it a different color so we know kind of what's going on. So once I do that, 3 times 4x becomes 12x. 3 times 5y becomes 15y. And 3 times 35, 3 times 3 is 9, which means 3 times 30 is 90. And 3 times 5 is 15, so this becomes 105. So you want to go with that smallest multiple, like where's that going to get you? So you don't get humongous numbers. 4 times negative 3x would be negative 12x. So created that additive inverse. 4 times positive 2y would be 8y. And 4 times negative 9 would be negative 36. So now I've created additive inverses here to eliminate. So once I eliminate, those eliminate. 15y plus 8y would be 23y. And 105 plus a negative 36. So if I take 5 off, down to 100, and then I take 30 off, I'm down to 70. And then I got to take 1 more off because I need to take a total of 36 off, so I'm at 69. And if I divide both sides by 23, I'm going to get y equals 3, right? Because 2, 4, 6, and 3 times 3 is 9, so y equals 3. Just a little wider for us, right? So coming back up, I'm going to put y equals 3 into one of the original equations. So here, I took these original equations, I multiplied them by something, and I made the system which had things that I can eliminate. But when I'm going back to find that second variable or to check my work, I don't use these new equations. I use the original equations. Because what if I made an error here? And then I used them to check my work, it would tell me that it wouldn't catch the error. It would just tell me that I'm correct. That's why I have to use the originals. So I'm just going to use the top one. So 4x plus 5 times 3 equals 35. Just change that back to blue real quick. And so when I do that math, still get 4x. 5 times 3 is 15. Still have 35. And I'm just changing the colors back just because, remember, we made it purple, so we kind of understood that we were doing that double multiplication. So here I'm going to subtract 15 from both sides. I want to be left with 4x equals 20. And of course, if I divide both sides by 4, and of course, I'm not writing that in divide by 4, but you certainly could, x equals 5. So based on this, our answer that we come up with is the coordinate point of x equal 5 and y equal 3. Now remember, I used the first equation when I did this last set when I found the second variable. So I'm going to use the equation I hadn't used. So 5 times negative 3 would be negative 15. 3 times 2 would be 6. Negative 15 plus positive 6, yeah, that would give me negative 9. That would be a true statement. Therefore, this answer is accurate. Okay, so that is how we do solving linear systems using elimination. It's a little bit quicker than using substitution, certainly quicker than graphing. We're going to go down and we're going to do 2 problems real quick about what does this look like when we aren't getting a standard answer. Because remember, usually we get a coordinate point. That's where they intersect. That's the common solution between the 2 equations. But what happens if they have more than one common solution? Or what happens if they have no common solutions? What is that going to look like when we do the math? So go down to page 3 of the notes. So here, if these look familiar, it's because we did these same problems using substitution. when we did the substitution notes, and now we're going to talk about what they look like with the elimination notes. So the work on this, we have x minus 2y equals 7 and negative x plus 2y equals 7. Well, if we eliminate everything, this is 0. This is 0. We'd wind up with 0 equals 14. And that is most certainly a false statement. Remember, when we have false statements, that means no solutions. If you go back and check your notes for substitution, in fact, this was a no solution. That means if we were graphing them, they would be parallel lines. If we were doing substitution, we would get probably, I think we got negative 7 equals 7. But here, because we're eliminating, boom, boom, they eliminate out, we get a false statement. So that's really quick when we're doing them using elimination. So we just got to make sure the problem is set up appropriately. Now in this one, remember the rule is we're supposed to be in standard form, and this is not in standard form. Standard form has x and y on the same side. So what I'm going to do is I'm going to take the second equation, y equals 8x minus 1, and I'm going to put it into a pseudo standard form. And I say pseudo standard form because right now I'm not worried about those rules in standard form that say that a, which is the coefficient of x, has to be a positive number. Okay, I just want to get it all the x's and y's on the same side. So I'm going to subtract or add, in a sense, a negative 8x to both sides. Okay, and when I do that, over here I'm going to wind up with negative 8x plus y. Over here the x's cancel out and I still have that negative 1. Okay, now I have this and I have negative 16x plus 2y equals negative 2. So still not at the same form. So I'm going to take negative 16. I'm going to take this one here. And because I have a negative 16x and I have a negative 8x down here, I'm going to multiply this by a negative 2 to create an opposite situation. Right? Those additive inverses that I need to create. Actually, the whole equation. So once I do that, I now have 16x and a negative 2y equals a positive 2. And if I bring down this one right here, right, my original, so all of this was us getting or altering the equation to find an additive inverse and get in standard form. So the other original was negative 16x plus 2y equals negative 2. And you can see, once again, these all are going to eliminate 16x, negative 16x, negative 2y, positive 2y. So I'm going to be left with 0, but 2 plus negative 2 is also 0. So this would be a true statement, which means I have infinite solutions. It's also, if we can put that 8 on its side, that's the symbol for infinity. We can also call it all solutions because it means every coordinate point on the line will satisfy both equations, right? And lines are never ending, so that's why there are infinite number of points on there. If we looked at a graph, we would only see one line because they'd be sitting on top of each other. Okay? So those are the notes for elimination, final method for solving systems. So if you have any questions, let me know, and we will talk soon. Miss you guys. Hope you're having a great day. I can figure out how to stop sharing.